Recording is on.
Okay, hey everybody. So, in this session, we are going to discuss a couple of tree problems. So, we discussed in the last weeks, we discussed tree BFS, DFS, depth first search and breadth first search algorithms. This week, we are going to touch base on these two problems, which is binary trees, level wise linked list. Some binary tree, and then how to return basically create a linked list of nodes at each level. It looks like BFS, breadth first search, where you go to each level by level, but we need to return a list of lists. So if binary tree of depth D, that means if you have D levels, we will get D linked lists. So this is one of the question from cracking the coding interview. So we'll discuss that, and then we will deep dive into the binary search tree. So what is binary search tree, and how how it is different from normal tree, and we'll see how to find an element. So that's the problem we are going to discuss today. Okay, let's start with the level wise. Okay, um, I'm going to use this writing tool here. So basically we want something like this. We have something like let's say A, B, C, D, E, and let's say F, G, H. Okay, so this one has three nodes. So we need linked list of lists. So basically the result will be something like this: a list of all the lists. There is one more list here, there is another list here. So the first one has only A, and the second one has B and C. So next one has B, D, basically D, E, F, G, H, all the way to the H, right? So we want to return this kind of data structure. So how can we do this? It's kind of very straightforward question in Java or C Sharp. So it's not basically what I'm saying is it is a BFS, right? So we are, it's not, if it is, what is the BFS answer for this? Breadth first search print. If you want to print in a BFS, it will be like this, right? A, B, C, D, E, F, G, H. Correct? So it's just a single. If you are asking me to, print the output in a BFS, it's just a single, everything in a single, line, right? Just outputting the elements in the BFS order. But if someone is asking, hey, I don't want in a just in one line, I want in a list of lists. So that is the difference here. So what is the data structure we use for BFS? Because level by level, right? So what is the data structure we discussed last time? Can anyone tell?
Q.
Q, right? Yeah, exactly.
Yeah, it's Q. Yeah.
So Q is the best data structure to execute the to traverse the tree in a breadth first traversal. But we can use Q here, but the intention here is we need to use the linked list. Well, not linked list. The C Sharp provided, C Sharp or Java, they already provided a list data structure, right? Which is internally, which might be internally, implemented using linked list or whatever. But we already have that data structure. So in that situation, we can leverage those data structures in C Sharp or Java or whatever the higher language. So we can directly use them in rather than using the basic Q data structure. Okay, that's the main difference here. So how it works is, so you guys know what I'm saying, right? So let me, maybe if I open this, I can show what is, who knows C Sharp little bit. Anbu, are you in which language you working? Like which technology?
Yeah, I use Python, so but I
Okay.
can still follow at least if I can understand the concept.
Yeah, it's just
That's not a
similar
problem.
thing. Yeah.
Yeah.
So I think Karanya, you worked on Java, right? So this is what I'm talking about, the list of nodes. So we already know node, right? Here is the node class. So node class has these values here, like basically value, right and left node, and here is the constructor. So the question here is level wise linker list. So level wise lists basically. So we are sending a route here, and we need to send the list. Each list here, list of node represents the inside node here, inside list here, A, B, C. So there are three lists here, right? And all these three lists are putting in a outer list. So this is basically a basically BFS algorithm using list data structure. So list data structure provided by C sharp. So similarly, there will be another collection. Basically, this is a collection, right? What is a similar data structure in Java or in Python? Any idea? What is that? Anbu or Karinya?
So,
Yes.
so this is like a linked list you're talking about?
No, this is not linked list. Just normal list of, let's say, list of integers, list of employees. Like we
Oh,
usually.
that is like in Python, they have something like a list.
Oh yeah,
So,
similar name.
mm-hmm,
Okay.
mm-hmm.
Okay.
Yeah, yeah.
No,
List, they
I
call
don't
it list data structure. Yeah.
exactly list data structure. So I think similar thing in Java. I don't remember exactly. There will be similar one in Java as well, collection or list or something like that.
Mm-hmm, mm-hmm.
Yeah. Okay. Yeah. Karnya, are you there? So I just want to know. So will you be able
Yes,
to?
yes, yes, I'm
Yeah.
listening.
So is you work in Java, right?
I'm working in JavaScript and Java.
Oh, JavaScript. What is the data structure name similar to this list?
I'm not aware of it.
Hmm.
So,
I think
sorry.
we can see. I
I
think
have
list. No problem. No problem. We'll see. I think list in. I think list. It will be just list, I guess. I'm just seeing.
actually, I have looked into the problem before the session began, and
Okay.
I couldn't get to this part. That's the problem. Yeah,
You get to the part means like you understand the problem.
this list of list.
Yeah. Yeah. So it's a list actually in Java also the same thing. Interface list collection. It's a similar thing. So yeah, this is what we are tackling here. So how can we do this? Is basically. The algorithm goes like this, right? So can anyone tell like how any idea like without using queue, how can we do this?
Okay, without using queue.
Without using queue, we can use the list data structure from Python or Java, whatever. So basically, if you use list, right? If you use list, we can put it in the list. We can put A there, and then we can put BC. But we should not put in the same list. We need to create another list, and we need to put BC there, right? So
But how about like a stack?
stack never works in it may not work in BFS, right? BFS we need to go level by level. So if you are putting
Correct, correct. Mm-hmm.
you're putting in a stack, let's say you put A in the stack and you remove the A, and you print A or putting a in a list. Okay. Now, after removing A, right? So now what you need to do is you need to put the children of A. So you put the B here and you put the C.
No, we can do like a C first and then D
We
second,
can
right?
do
Like a,
that. We can do
so
that.
we
That's
can
right.
instead of going from left to right, you
Yeah.
can take the right to left path.
That's good. That's good. Now what happens is now you put C and B, and then
Mm-hmm.
you're done with that, and then you pop the B out. You pop the B out,
Mm.
and you put B in a separate. At this point, the problem here is you don't know when you need to create secondary list, because
Mm-hmm.
you put A here. Now you are popping another element. You don't know whether A belongs to this level or this level, because you're not putting that
Mm-hmm.
context here. Probably what you need to do is you need, in order to put the element, you may need to also say, hey, this is at second level, B is at
Mm-hmm.
second level.
Correct, correct.
If you add the some context saying, oh, this is not the first level, so I need to create one more list. So when you are popping out, maybe you need to create another context also saying, hey, this should go to the separate list. Now you created the second list and you put the B there. Now at this point, once you pop the B, at this point you need to process the children, right? So what are the children? D and E. If you are following the same pattern, you put E here and then you put D here, right? If you're following right to left pattern, because you inserted C and then you inserted B, right? Similarly, you are going to push E into the stack and then D into the stack. Now you are done with B. Now you are popping another element D, and you are going to say D at the third level. D at the third level, right? So, but maybe that's another pattern of doing it. So you don't insert here, you don't insert on the second list, you insert in the D in the third list. If you have that context, otherwise what happens is you will put everything like this: A, B, D, and then E. So it's something like it's giving a DFS. It's you are going to depth first search order, right? Unless you put the context. Are you following, Anbu? Is it clear?
Yeah, I was looking for the mute button. Yeah,
Yeah, no problem. So
I got
unless
it.
you store extra context here, which level are you in, and otherwise what happens is we don't know in which list you're going to add. If you're adding in a single list, what happens is it will end up in a DFS manner, depth first search, because you're going like A, B, D. You're not going like A, B, C, right? So that is the problem. It's not a problem, it's just another, it's a good example, we can use it, but only thing is you need to you need to store a node and also the level of the node in the stack. Okay, so I'm going to explain another simple way of achieving this. Okay, so let's say I think let's take the example here itself. I want to take the same example rather than ABCD. Okay, I'm going to erase this. It says 9 here, and 5 11, 5 11, and then 4 6 10 12. 5 has 4 6 10 and 12, and now 8 and 14. This one has 8, this one has 14. Okay, so now we have 4 lists, right? We need to create one list for each level, correct? So what we are going to do is we are going to take two lists temporarily, like let's say L1 and L2. Okay, so these two lists are operating lists. These are the lists we want to operate the entire tree. Of course, there will be a resulting, as I said, there will be a resulting list of lists. So here we are going to, this is a result. Okay, here we are going to put those lists. Once you create the list, we will put it in the result. Okay, so now in the L1, what we do is first we will initially insert the root there. Okay, you can think of this as previous list, and let's call it like that. This is a previous list, and this is a next list. Okay, this is a next list. Previous list we are putting 9 there, and next list is empty right now. Okay, now our algorithm process the previous list. Hey, what is the elements in the previous list? Give me the elements in the previous list. Okay, and I will process those elements. Okay, now there are how many elements? We have only one element, right? So we'll process it. We don't remove anything from the previous list. Okay, we'll process the 9. How many elements for the 9? 5 and 11 are the children, right? So we will put those children back into the second new list. Okay, 5 here, 11 here. We will see, do we have any elements in the previous list? No, there is no more elements in the previous list, correct? So now what we do is we will store the previous list into the resulting array. That means we are done with processing the previous list. We will store the resulting list 9 here. This list will be here. Now this previous list is completed. We process it completing previous list. Correct? Now what we do is simply we reassign this previous list to new list. That means we are overwriting that variable. Basically, this is just two pointers kind of thing, right? Previous list points to this list until now. Once you add that list back to the collection of resulting list, we will say previous is equal to new list. This is the new list, right? So now both will point to this one. But when you come back to the loop, this is a kind of looping logic, right? When you start the loop again, what happens is, so we will take this one as, this is the previous list right now, and the new list is empty. We'll start with empty again, new list. Okay. Now we will process 5 and put the children of 5 back into this queue. 4, 6, and then we'll process the next element. Okay. 11. What are the children of 11? 10 and 12. Okay. Are you guys following so far?
Yes.
So now what happens is, we completed processing the previous list. Exact same thing. Once you complete the processing of the previous list, we will put the previous list back into the result here. Here is the result. We completed 5 and 11 processing of this list. Now simply point previous list is equal to new list. That means simply previous list, this becomes previous list, and then new list becomes null. So now the same thing will appear, right? So the same logic. So now this is the previous list. This is PL, and this is new list, NL. Okay. Now we process 4. There are no elements for 4. There are no children for 6. And you process 10 here. So now for the 10, we got children 8. And then there is no more children for 10. And let's process 12. There is a children for 12. We completed processing, the same thing. Then the resulting comes here, and then next 8, we process the previous, this becomes previous list, and there are no more children, so that will also come here, 8 and 14. Okay. So we are essentially doing the same thing as a queue, but in queue, everything in a single list, the list or whatever the data structure. Let's say queue data structure, we are putting in one direction rare, and we are popping it from another direction. So since if you are putting everything in one list, we don't know whether 9 and 5 here, we don't know how far you need to go for the first level. As I said before, as I said, Arnav, Anbu said, like, we can use stack or queue. We can use it as long as you are storing that context. Hey, 9 is at the level 1, so you need to store extra information in addition to the actual node. You need to put 9 and also say, hey, 9 goes to first list. You can put 5 here. You need to say 5 should go to second list. So you need to store additional information while popping, while removing, while dequeuing the elements. We can see, oh, this 5 goes to second list. Let me create another list and put the 5 in the second list. Don't put it after 9 in the first list. So now we will get the 11 here. Once the 11, oh, this also belongs to second list. Let me add to the second list. So that kind of little bit logic we need to do, which is also good. Like, that is another solution. Actually, now I realized that is also a good solution, not a problem. We can still use the queue or a stack, but you need to store additional information along with element. But here, if you use two lists, right, it's very easy. So basically, you're creating the previous list, and once you process the previous list, that previous list you can simply add to the result list, and then you're basically swapping it out. You're swapping the previous list with the new list you created when you processed before, right? So this is the logic. I can show you the code if you understand. Are you guys following so far? Right?
Each list is disconnected in that way. The array of list which we have shown as the result.
Yeah, that's what they want, right? That the main question itself is like the disconnected. Like so if you look at the question, create given a binary tree,
Okay.
create linked list for nodes at each level. If binary tree has depth t,
Oh,
we will get d linked lists. Link
okay.
we can d linked list means like d is like number of depth. If you have 4, we will get 4
Um,
linked lists. So it's a disconnected different lists.
yeah.
That's it. It's
Okay.
not a single list, right?
Yeah.
That's the question. So I think it is in the page number 224 of the, I don't know which version of CTCI I have. That That's the question I have. I think if you go to CTCI book version 6, I think so. That's the question, interview question. So now, yeah, we need to create these distinct lists here, and here is the code as I explained. So we have node here, and this is the main method where I created all the nodes. 9, 5, 11 is exact same. I'm basically building the tree here, and here is the main label said list of nodes. Okay, so what are we doing here is this is the result list. As I said, we are simply creating the result first. So the kind of empty, first initially it will have empty elements, list of list nodes. Now previous list. As I said, we will create a previous list and we will add the root into it. And as long as previous list dot count greater than 0. So as long as previously, if the previous list is if the previous list becomes null, right? Because if you look at here, when you are processing this, the last iteration, if you come to the last iteration, so this becomes previous list and the new list equal to empty list. There is no elements. Now you process 8, you cannot add anything to the new list because there is no children for 8. If you process 14, there is no children for 14. So finally, the new list is empty. And since you completed processing 8 and 14, you put the previous list into here, right? And then into the resulting list. And then you said PL equal to new list. So now this is the previous list for the next iteration. So this empty list becomes the previous list, which have 0 elements. So that's where our loop stops. So previous list dot count greater than 0, do this. If the previous list doesn't have any elements, let's say you sent null, so there is nothing, right? If I think we should add that condition. If the root is null, there is nothing to do. So similarly, if the previous list has 0 elements, you're done processing all the elements in the thing and you exit the loop. Otherwise, what we do, if there are elements in the previous list, simply we are first adding that previous list back into the result. So as I said before, like you can just simply add immediately before processing or after processing, doesn't matter, because by the time you come here, we already have a previous list with element 9, and then we'll put it there and then start processing that elements. So we create a new list. As I said, we will create a new list, and every element we will process for each is a common loop, right? So for each element of previous list, do this thing. What are we doing? If the element dot left not equal to null, add to the new list. If the element dot right not equal to null, add to the new list. We add left to the new list, add right also to the new list. And once you complete the whole iteration, basically this whole iteration will work. Let's say if you have 10 nodes here, if you have here 4 nodes, right? If you look at this iteration, like 4, 6, 10, 12, we have 4 elements. All these 4 elements, we will see if we have any children for 4, if we have any children for 6, if we have any children for 10 and 12. So if we have any children right or left, we simply add to the new list. That's what we are doing here. If we find left, put it in the new list. If you find right, put it in the new list. Once you're done processing, we are replacing previous list with new list. This is the main condition here, because you added previous list to the result, so it's okay to overwrite. And you also completed processing of all the elements, all the children of that the elements in the previous list. So now it is safe to overwrite the previous list variable with the new list. Okay. Hi Shivank.
Hi.
Hey man, welcome. So we are discussing a problem in the cracking the coding interview book. Okay.
Yeah.
Since you just joined, I will give a little bit explanation. So basically what the ask here is, given a binary tree, we need to create a linker list for nodes at each level. That means if a particular level has 4 elements, you need to create a linker list for that 4 elements. Okay. and if the binary, like for example, binary tree has depth of D. So let's say the binary tree depth is D, we will get D linked lists. Okay. So
Sure.
it's kind of BFS. It's kind of breadth first search algorithm. So I'm explaining using a linked list or list data structure in C sharp. So we can also create linked list, I think, but we need to. Yeah. So basically, this is a list of lists. So this is a resulting list. We need to have something like this: 9 here and 511 in mid different. 9 here and 511 is second, and 4 6 12 10 12, these are in a third level, and 8 and 14 in fourth level. So we will get 4 linked lists: 1 2 3 4. That is the main result of this algorithm. So I'm explaining algorithm here. Basically, we will create, this is the result is a list of lists here, and by taking a previous list, what we can do is we can add the root there, and then we will process the elements in the previous list. So initially this is the previous list, and previous list
Suresh,
we had. Yeah,
yeah, what's the page number in coding cracking the coding interview book?
it's I noted as 224.
Good.
um I don't know which, I think I have the version, sixth version, I think. I need to look at my bookshelf, but yeah, if you look at the trees, if you look
Can
at.
you explain the test case once more? I didn't get the question.
So the question is basically, we will given a binary tree, we will get a binary tree. We need to create linked list for nodes at each level. So that means we need to create a list for each level. Okay. For each level means, like if you look at this example, right? How many levels we have? We have 4 levels: 9 at the first level, 511 at the second level. Correct?
Yeah,
4 6 and 4 levels. So we will get 4 linked lists. Basically, the result is you need to create 4 linked lists. For each level you need to create one.
yeah,
That's what it says.
got
That's
it.
what it says. Like if the depth of the binary tree is D, we will get D linked lists.
Yeah,
That's
got
it.
it.
So I created I think I should try again creating a real normal linked list, but I'm creating a C sharp list of lists. This is also similar to that, right? So basically, this is the result list. In order to execute this algorithm uses two linked lists. So basically what I'm doing is, we'll create previous list and next list. Okay. Initially in the previous list we will put the root node, which is 9, and then we will loop it until the previous list is 0 elements. So now we have one element. We'll process the 9, and we will put all the children in the new list. Okay. So initially we will add the previous list into the result list here. That's what we are doing here. So we added root here, and then simply we'll put the previous list into the result list. This is where we want to return. And now creating the new list, and we are putting all the elements, all the children of next level. Basically, these are all children of next level, right? We are taking each element from the previous list and see, do we have any children? Do we have any left? Do we have any right? If we have left, put it in the new list. If we have right, put it in the new list. That way we processing all the elements in the previous level. Once you process it, we simply say previous list equal to new list, because you completed processing of the previous list. You already added to the result and you processed here. So we are simply overwriting. Basically, we are saying, hey, since you processed this one, now the previous list becomes this one. Now the 5 and 11, so that becomes the previous list. Now 5 and 11 becomes the previous list. Oops, it's really big. Yeah. Okay. So now previous list becomes 5 and 11. So we will process the same thing. Process 5, put all the children in the next list. So now next list becomes 4, 6, 10, 12 in the next iteration, right? So that's what it is. This is very simple algorithm with the 2 loops. One loop is for the previous list, and also another loop is also previous list. One is like we are processing elements, and first one is for basically adding or terminal condition. Like if we don't have any elements in the previous list, that means you're done processing the entire tree. Okay, so it's a level by level algorithm. It's a simple thing. Let me run and show you. So here what I'm doing is, once you complete the algorithm, I'm just iterating to the list here, result here, and in the level list, this is the level list. See, this is the result, right? So if you look at the tree here, 9 will be in one list, 5 11 in second one, 4 6 10 12 in third one, and 8 4 8 14 in the fourth one. So there are four lists here in the result. That's what we are showing here, right? So the result has 4, and level list is one level. So this is the level list. So that means for each level we'll have the nodes. So we are printing in a controller, write will print in a single line. When you say write line, it will go to the next line. So once you complete printing 9, it will go to the next line. And again, once you complete printing the elements of the second level, 5 11, it will create new line. So basically there are 4 lists in this result. Okay, so you guys can try, rather than using this one, maybe you guys can try creating a normal linker list, right? So we discussed about normal linker list, so you can add each element. So we discussed about adding element in the linker list, right? Normal linker list. Adding element in the linker list is a little tricky because you need to start from head again. Every time you need to start from the head of the linker list, right? You need to add at the rear of the list, right? So I don't know whether it's following. So let's say you want to create linker list for 4 6 10 11. What you need to do, you need to create 4, and 4, and here is the head points to the 4, and then you need to create 6 at the end and update the linker list, right? Again, if you take 10, so you need to start from head 4 6, and then add at the rear, and then create this create this address mapping. So since it is a really big problem, because this itself is a separate problem, right? Adding an element at the end of the linker list itself is a separate algorithm. So I think if the interviewer asked about this question, the main question here, I don't think they are asking about normal plain linker list implementation, because it will take time. So you cannot complete this algorithm along with the other algorithm, along with this creating the plain vanilla kind of linker list without using any existing data structure from Java or C# or Python. So that becomes really maybe 2 hours kind of algorithm, 2 hours kind of interview question. Basically, I don't think that's what they're asking. So you can simply use existing data structure in your favorite language where you're writing the code. Basically, you need to put this kind of logic there. So cool, that's the main algorithm, first one. So any questions in this before jumping into the binary tree concept, binary search tree?
No solution.
Yeah, so that's great.
It's clear.
Thank you. Yeah, someone is asking something. Shivang, is it clear? And Anbu?
Yeah, it's clear for me. Yeah.
Yeah,
Great.
to see the
Yes.
code. I'll check
Yeah,
the code.
I will show the code. I will send the code. Yeah, no problem. If you have any questions, let me know.
Yeah, fine.
Yeah. Cool. Yeah, and then we will go to the next one, binary search tree. So we know that, I think we discussed in the beginning about binary search trees. So anyone can tell what is the main difference between binary tree and binary search tree?
Binary search tree is a sorted tree
Mm-hmm.
where the left descendants are less than the root, and the right descendants, the whole right descendants, are greater than the root.
Exactly. That's the main difference between, and why we need to do that. What is the, why can't we go with the normal tree? Why we need to use binary search trees?
Uh, to search fast.
Mm-hmm. That's a good example. That's a good answer, because in a normal tree, if you are building something like this, right, we just discussed here. So in order to search 8 or 14, you don't know where to start. Like 8 could be in either this side or this side. You need to search every node. Either you can follow depth first search or breadth first search. So until you process all the elements, you don't know whether 8 is there or 14 is there, right? So if it is in a binary search tree, because the binary search tree follows the pattern, as Karani mentioned. So all the left nodes are smaller, all the right nodes are greater than the root. So that will give you at least half of the things, right? You don't need to search one part. Once you find out, hey, where to go, you need to go left or right. Based on the value, you can decide. So that's the main advantage of binary search tree. So I will give you an example, and I will show you. So here is okay, binary search tree. Here is an example. Yeah. Or did I write here? No. I can build a tree from this. So here is an example. So we have node 15 here. Let's try to write down here. So we have 15. Okay. And 15 has left node 3 and 17. Here is 3 and here is 17. And 3 has 2 and 14. 2 and 14. Okay. And 17 has 16 and 18. 16 and 18. So this is a binary search tree, because this is how it is, right? This is the rule. I think like left node less than or equal to right root. This is root less than or equal to right node. Okay, this is left and this is root and this is right. So some people will say this will be, these two can be equal, or in some of the definitions you can have left and root will be equal. But let's look at this example. There is no such kind of number, so we are good. So if you look at here, if you take any three subtree, right, if you take any subtree, let's say if you are taking this particular subtree, let's say we took this subtree, right? It follows the same pattern. So 2 is less than 3 and 3 is less than 14, right? And if you take this, even this one, it follows the same thing. 3 is less than 15 and 15 less than 17, right? That's why it is binary search tree. Okay. And another thing is, by using this example, we can also easily say that all the elements, because if 3 is less than 15, right? So we can say like every element, not only this, just the descendant, not only just the child, all the elements in that subtree is also less than 15. So what I'm saying is, see, look at here, 14. 14 is less than 15. That's why it is here, right? So all the elements on the right subtree is also greater than the root. It's not just left node or right node, right? So that's the main definition here. So now and another thing here is binary search tree. There is if you want elements in a sorted order, right? Can anyone tell what traversal is best suited? So what is the sorting order of this one, right? So we need 2, 3, 14, something like that. We have
It should be
different
2,
traversals.
3,
We have
14, 15, 17, right? Oh, sorry.
yeah. We
2,
have this is one
2,
way
3.
of doing it.
Yeah,
We have DFS,
correct.
another way of.
Yeah.
What are the other ways we traversal? We already discussed about, right? We have in order, pre-order, post-order.
Mm-hmm.
So which traversal will give you these?
Pre-order. Pre-order.
Pre-order. Okay. What is pre-order?
Oh, no. Sorry. So it should be like left, root, right? So that will be like in order.
Exactly. In order. In order will give you that. In order, if you follow in order traversal, it will give you in a sorting order of elements, in a kind of increasing order of elements. Okay, so are you guys following? So if you take in order, right, in order means left node, root node, and then right node, right? So you should not take 15, you need to go all the way to the left. 3, you should not take 3, you need to go to the left node. Okay, 2, there is no more left or right for 2, so we will print 2. Now root means 3. Now right, which is 14. And then you're done with the subtree, you go to the right, because you're done with left. Now you go to the root, which is 15. Now you go to the right, and again the same algorithm works. You should not print 17 yet, because you need to process left, root, right. So left means again 16, and then root, then 17, and then 18. So that is the sorting order of the elements, right? Are you guys following so far? So
Yes.
in
Yeah.
order will give you in the binary search tree, this is the binary BST. So in the binary search tree, in order will give you, increasing order or sorting order of elements. So now let's assume we need to find an element. That's what the next algorithm, right? Now we discussed about the how the binary search laid out, and how the elements are, inserted in the, not inserted, how the elements are configured or inserted, yeah, and how the elements are inserted in the binary search tree. Now we have binary search trees available. So we'll talk about insertion deletions in the coming following weeks, because those are very tricky algorithms. If you need to insert, we need to find the right location. Now let's talk about just finding the element. Okay, so now this tree is just how many elements? 6 plus 4. We have only 3 plus 4, 7 elements we have, right? Only 7 elements. We can look at this tree, and we can say, do we have 16 in the tree?
Yes.
Yes, because we can simply see just seven elements, and the tree is just right up, in front of our eyes, and we can say 16. But if this tree has 10,000 elements, you cannot even see, and it is in the data structure, in the database, in memory. So how can you find it? So you don't need to go to every level. You don't need to look at all the elements. As I said, the binary search tree, that is a beauty, right? You can start from the root. Let's say how you found 16 was there. So let's say we follow the same pattern. Let's say you want to find 16. So always start from the root. You know that 16 is greater than this value, right? 16 is greater than 15. That means according to this rule, if 16 is there, it will be in the right side of the tree. That is the main difference, right? So advantage of using binary search tree is faster finding. So you no need to search anything on the left subtree, because it follows the binary search tree rules. So it will always be in the right subtree. Now you want to search 16. Now you come to here. Now we'll see, is 17 equal to 16? No, 17 is not equal to 16. So now where to go? Because the root element is greater. If 16 is there, it will be definitely on the left side of 17. It definitely somewhere here. It could be another 1,000 nodes. We don't know. It could be another 2 nodes or 3 nodes. So we need to travel. We need to travel to the left side, because root is greater than what you are looking for. Now you come here, 16. Okay, we found 16, and they will say, yeah, we found the element. You need an employee with employee ID 16. Yep, we found it. Here is the object. Take it. Right. So now let's say I want to say, do we have 12 here? If we are say find for 12, we follow the same pattern, right? Start with 15. Is 15 equal to 12? No, 12. This is false, right? So now what you do, and then if these are not equal, then you compare with which one is greater. Is 15 greater than 12? Yes. If it is greater, you will take to the left side of the tree. That means if 12 is there, it will be somewhere in the left subtree, right? There is no way that 12 will be on the right of 15, because if you are putting 12 on the right side of the 15 somewhere in the right subtree, then it's not even BST, right? So the insertion will take care of the inserting at the right place. So that's why when you are searching, you can safely go to the left side for 12. You no need to worry, because if someone is inserting 12 on the right side, that insertion algorithm itself is wrong, right? We will write algorithm in such a way that it should never what is that vomit, or like it should never follow, if it should always follow the rule of BST. That's what I want to say. So when you are inserting element, you need to make sure it follows this pattern, follows the rule. So now you are finding 12. Okay, now 3. You went to the left side and you came to the 3. Is 3 equal to 12? No. Now you will see 3 is greater than 12? No. If the root is small, definitely it could be right side, somewhere in the right side, right? So now you go to the 14. Is 14 equal to 12? No. Now you will see, do we have any elements for the any children for 14? No, there is no children for 14. Now you end up completing the search and you don't have 12. So then simply we'll return saying, okay, we did not find 12 in the tree. Okay. Is it are you guys following so far, or any questions?
Yeah, but Suresh, how far the searching and sorting is reduced comparing to the binary tree?
How far the searching and
Searching
sorting?
for, yeah, searching
Uh,
is reduced. Actually, the steps uh, before we have to visit each and every node 15, 3, 17, 2, 4, and then 16. So now we are finding it in 3 steps.
exactly.
What's the time complexity of this?
Yeah, complexity. We'll look at the complexity. So yeah, that's absolutely correct. So the main thing is basically it will improve the searching, right? So can anyone tell the complexity? Complexity of finding an element in the BST.
N by 2
It will be
So
n by
maybe
2.
like height of what they call like
or log n?
height of the tree maybe.
It is log n, I think. So
Yeah.
complexity of BST find. I'm just searching here. So difference operations. It's log n. Complexity of binary search tree is basically log n. So I'm just finding a good resources here to explain the complexities. See, so the time so the binary search tree is a balanced binary search tree. The height of the binary search tree is becomes log n. Okay, so the time complexity of BSC operation is order of log n. So what they are saying is, if the binary search tree is like this, see this 1, 2, 3, 4, 5, 6, 7, like it is equal to the number of elements, right? It is a binary search tree because every element is greater than the root. Every child is greater than the root. It is binary search tree. If you look at the algorithm, what is the complexity of this one? Let's say you want to find the worst complexity 7. If you want to find 7, how many elements you need to reach? You cannot jump to 7, right? You have to go to 1, 2, 3, and we have to compare 7 with every element, saying this is not 7, this is not 7, 4 is not 7, 5. So it's kind of, in the worst case, you need to meet all the elements. In this binary search tree, it is order of n. So in the worst case, the binary search tree is a squid. What is that squid? I don't know this word. Squid binary search tree. This is squid binary search tree. The height of the binary search tree becomes n. What is the height of this tree? N. That means 7, right? So the complexity is order of n. But this is not the balanced. This is not balanced binary search tree. Balanced in the sense, like there is a separate algorithm for that. So balanced in the sense most of the elements and right elements and left elements are equal. At least they differ by one level. That's it. So something like this. This is a balanced, right? You are balancing the same elements 1 to 7, but you balanced it. Instead of saying 1 as root here, you put 4 as the root. That way, what is the advantage here? If you are putting 4 here, finding 7 is easy, right? Finding 7 is just 3 steps. You no need to compare 1, 2, 3. You compare just what is the value 4. Okay, you want 7, come back here, and 6 equals 7. No, let's go to the 7 equals 7. So it reduces a lot. But is it 3? You cannot say 3. It's a level 3. That is basically log n. Log n is the height of the, it's not height, basically log n is the complexity of the finding an element in the worst case if the binary search tree is balanced. So that's how it is. So to gain better understanding about time complexity of BST operations, so he's asking us to download this. So if you can see, look, I can send this link. It's very interesting. So they clearly explained. So the time complexity of the binary search tree. Before you go through this article, make sure you have gone through the previous article on the BST operations. That is also good thing. So commonly preferred operations on the binary search tree, as I said, searching operation, insertion operation, deletion. These are very common. So time complexity, they explained as time complexity of all BST operations, order of h is height of the binary search tree. So that's the order of log n. Yeah, they are explaining all the insertion and everything. So anyway, so log n is the complexity of BST. Okay. So now I will show you the code of finding an element. If you guys are clear with this, okay? Karanya, shall I go with the code?
Yeah, please.
Okay, so here is the binary search tree. So here is the thing: print in order, print in order, in sort order. So basically, I'm just printing here, but if you look at it, is just in order traversal. As I said, printing of a binary search tree in the sorting order is equal to printing in order. So simply saying root dot left, if the root is null, written. Otherwise, go to root. We are calling the same method, which is recursive function. Root dot left, console dot right value, and then root dot right. So it will print all the elements in a sorting order. Now find node. I want to find 16 here. Do we have 16 in this? We have 16, right? So now finding 16, as I said, very simple algorithm. First, we will compare with root. If the root is null, man, you sent a root with the null value and you're asking me to find 16. No, it's not there. It is base condition, right? If the root is null, you simply return false. Okay. Otherwise, as I said, we will compare if the root value is what you are looking. If the root value, let's say you said 16 is on the top itself, you don't need to search any elements, right? So if the root value is equal to the value you are looking, simply return true. Yes, it is there. Otherwise, this is the condition. If the value is less than the root value you are looking, let's say if you are looking for 9 or something like this, if you are looking for 9, you need to go to the left subtree, right? That's what we are doing. If the value less than the value of the root, find the node in the root dot left. Now we are changing root. Basically, you start finding the element 9 in the root dot left. We are calling the same method. This is a recursive. As I said, starting from trees, we will use recursive a lot, recursive functions and recursive logic. So what are we doing? Basically, if the value is not equal to root, take the left value and start the exact same function, right? So ultimately, if you say, hey, find the 9, so there is no 9 here. Ultimately, you will end up having root becomes null and we'll say false. Now we are not there yet. In the second loop, what happens? If you are looking for 9, it will be 3 now. 3 equal to 9? No, 3 not equal to 9. Now we'll compare. Is 3 less than the 9? No, right? So 3, yeah, 3 is less than 9. Yes, that's true. If we are looking for 9, 3 is less than 9, then no, it's not 3. Basically, we are looking for value. Sorry, the value is 9 less than or equal to 3. We are comparing here. Is 9 less than 3? No. Then it will go to the right side. Then compare 14. Now what happens? So 14 less than, like a 9 less than 9 less than 14 here. No. Then root dot left. What is the root dot left? What is the left for 14? Is null. Right for 14 is null, and left of 14 also null. At that, in that situation, it returns the false. Right? So if you practice a little bit, it's easy. Like when you are practicing, you know how this works. So I can put some breakpoints if you want to see how this is working. Otherwise, we can run and see. Okay. First, let me run. So we are comparing for 16. We will find 16, and there is no 9 in the tree. We'll find false for that. Let's see, it's building there. Here is the output. See, we got 2, 3, 14, everything in a sorting order, and found 16. True. Yes. Did you find 9? No. So if you look at if you want to run with a debugging, you will see how it works, right? Is it clear? Is the algorithm clear so far? Finding an element?
Yeah.
Yeah, it's pretty easy, but only thing is you need to understand the basic logic, how this is working, everything. So if you look at here, the first value is 15. We started with value 15, right? So locals, so value. So what is the value is 15 here. So v equal to 16. Okay, we are finding the value v. We are looking for value 16, and the root value is 15. So now what happens? If I continue, yeah, is both are same. Value is basically 15, but the value you are looking for is the root value is 15, and the value you're looking for 16. So it come back to it goes to the if condition. So this is value is 15, and you're looking for 16. That means it has to go to the right. So that's what it's going to do now. See, now we are starting with 17. Let's see, because that's a 17 is the next root, right? So 15 dot right is 17, and you're looking for 16. So if I go to this one, see, we created another, it's like a recursive loop again. So you're looking for 17, and the value here is 17, and but the value you're looking for is 16, which is not equal to true. Now come here, and now it will go to the left, because root you're looking for 16, which is less than the root value. It should go to the left side, and that is 16. So in the next iteration, what happens? In the next iteration, it is 16 equal to 16, right? So you completely reached it. Basically, you started here. If I want to highlight, you started with 15, it goes to 17, you compared with 17, then it goes to 16. Now the comparison equals, the value here is equal to value you're looking. So then it returns true, right? It returns true, and it returns true for every other loop. See, it returns true because we put a return value here. So whatever you find there, just return that value. So it will return ultimately it will return the value. Oh, it is looking for the actually then our program is running for 9. So but anyway, so you guys understand the full algorithm, right? How this works and everything. Great. Yeah, any other questions? Let me know.
No, Suresh. But after this, we'll go on to solve problems regarding binary search trees.
Not yet. So in the next algorithm is I'm going to explain is how to insert an element, because we inserted element like this, right? Like let's say I inserted using this algorithm called left and right. I know where to put the elements. I created this binary tree using the elements, using the values I have. But now I say, hey, I want to insert value 17 or value 17 again, let's say, or value 20. So how to insert an element in the binary search tree? That is the next algorithm. Basically, you given a binary search tree, how to insert an element in the binary search tree and how to delete. Let's say if you delete 17, what happens? You cannot delete 17, right? You need to take another element here. You need to pull 16 or 17 or 18. Sorry, if you are deleting 17, you need to pick the which one is best. You need to put 18 here, 18 to that location, right? Then it follows the same pattern. So that's the thing. So how to delete an element? If you have, let's say, if you have binary search tree for our employees in your company, you are the CEO, you have employees of 1,000 people, and you put it in a binary search tree. Now one employee resigns and go to the another company. Now you need to delete that record. You need to delete that record from that employee record from your binary search tree, right? That's an example. How can we do that? Similarly, inserting new element and deleting new element. Inserting, let's say you got the new employee, you know, let's say you're putting an employee based on the age. You should not put at the end, right? So based on the age, let's say you recruit an employee with 40 years, so you need to find exact location and put it at that level, right? Or maybe based on the salary. There's a different conditions. Like it's not only, when you're creating a trees, you will follow what is the value you are using. Is it the value of the object? Is it like a salary of the employee object, or the age, or you can take any other parameters. That's the main index, basically, on which index you're putting your elements, right? So that is the main thing. So these are the two important. And then next question is finding in order successor. In order successor, I will explain what is in order successor. And this is also very important question in terms of interviews. And first common ancestor, this is also another interesting. First common ancestor, I will explain those. And here is another binary search tree is BST. Given a tree, binary tree, is it a BST? So this is also another question. So I will give you a tree. You tell me whether that is a binary search tree or not. That means we need to see whether it follows this pattern, this particular rule, or not. It can this any of the element in the tree can break the rule. If it breaks the rule, the entire tree is not a binary search tree. So how to find, what is the algorithm to find that condition? That's the main intention of this algorithm. Is a given binary tree is a BST. I will give you a tree. Tell me whether, write an algorithm, tell me which returns true or false. If it is binary search tree, return true. If it is not binary search tree, return false. Okay. And is tree balanced? This is also another interesting question. Yeah, I will cover this in the next couple of weeks. Okay.
Yeah.
Yes, sure.
Cool. Yeah, Shivank, any questions from your side?
No, it's fine for me.
Awesome, great. Okay, then. So yeah, I will let you guys take off then. So it's already kind of night for you, right? Where are you from, Shivank? Which location?
I'm currently in Bangalore, but
Bangalore. Okay,
I'm
okay.
from Delhi.
Yeah, I see you're in Delhi right now. Cool, cool. Yeah, it's already night there. So thank you, and I hope you got some understanding about these concepts. So I hope it might be helpful. So let me know if you have any questions. Otherwise, we'll take off and we'll meet again next week. Okay.
No, it's fine, Suresh. Thank you.